Okay, here is the second half of our naming lecture. And in this part, we're going to talk about naming molecular compounds as opposed to ionic compounds. The rules between these two things are completely different. So the most important thing is to be able to successfully tell the difference between molecular compounds and ionic compounds every time you are looking at a compound. That's why we spend so much time doing it, actually. Now, whereas ionic compounds combine together based on charges and the idea of forming electrically neutral compounds, the same thing is not going to be true with molecular compounds. So here's one example where you have nitrogen and oxygen, and you could just see the variety of compounds that the two things can form. It's not it's not based on ionic charges, right? They're sharing electrons in all of these situations. So we're going to define a molecular compound as something that is composed of two or more nonmetals. And when we write the name of a molecular compound, we're going to start with the element that has the smallest group number first, right? The smallest group number would indicate that it's like the most metallic. So this kind of follows the trend that we were using to name the ionic compounds as well, where we would put the metal first. If you have two elements that are in the same group, then you're going to write the element with the greatest row number first. And the prefixes that we're going to write are going to tell us how much of each element is present. Okay, the number of atoms present of a given element in a compound. So these are the prefixes that we're going to use to indicate that. Thank goodness they are the same prefixes as we were looking at in the hydrates section, so that's nice. And one thing you want to keep in mind is that if there's only one atom of the first element, and this is only true for the first element, the prefix mono can be left out. Okay, but for everything else, you want to indicate the prefix, and then the name of the first element, and then the prefix, and the name of the second element, plus that same IDE ending. All right, so let's go through these. If you'd like to pause it at this point and try them on your own, that would be a good idea. Always good to try it on your own. All right, so the first thing, if you were looking at this on like an exam type of situation, is that you'd want to run through these and make sure that each of them is a molecular compound. That's step one. So in this case they are. So now we want to go through and name them. I'm going to put the names up and then we can talk through them. So the first one is nitrogen triiodide. Notice that I did not put a mono in front of the nitrogen because it is the first element that we're naming. Okay. For B, phosphorus pentachloride. Okay, so there's one phosphorus, so I did not include the mono because the phosphorus is first. And I put the penta in front of the chlorine because there are 5 of them, and I changed the ending of my chlorine to IDE, right? Because that last element that we list, we're only going to use the root of the element name, and we're going to add the IDE ending to it. Okay, so hopefully the rest of these then make sense to you. Oh, let's erase that little rando line. And think about this question for a second. Okay, we have the compound NCl3, and the name of that is nitrogen trichloride. But AlCl3 is just aluminum chloride. Okay, and why is that true? Right? The first and most important difference between the two of them is the fact that NCl3 is a molecular compound and AlCl3 is an ionic compound. So we can tell based on charges that only one aluminum would need to combine with 3 chlorines to form a compound of aluminum chloride. That is based on charge differences. For NCl3, we're not basing the compound formula on charge differences. So we have to express that we have 1 nitrogen and 3 chlorines in the actual name itself. Another type of molecular compound that we need to look at are acids. Okay, these are molecular compounds that behave a little weirdly because they do form ions in water. Okay, so you're going to be able to figure out that something is an acid because you're going to see that there's going to be an H out in front of it. Okay, and then the second half of whatever is left over, that will be your anion. All right. An acid has to be aqueous, which means it's going to dissolve in water. Something cannot be considered acidic if it does not dissolve in water. Okay, so here are some typical characteristics of acids. You should know these. And I think a lot of them would make sense to you at this point. Acids generally have a sour taste. That's why even if you're eating some of your like Sour Patch Kids or something like that, if you were going to test the pH of those, you'd find that they're pretty acidic as far as food goes. Acids can dissolve metals. Acid formulas start with an H out front. And we're not going to consider something an acid if it can't dissolve in water. And there are 2 types of acids that we are going to name specifically. Okay, the first is called a binary acid. The second is called an oxy acid. Notice this part here. A binary acid only contains 2 elements in it. Binary, that means 2. So a binary acid will have 2 elements in it. It's going to usually be hydrogen and then another halogen. Okay, that's just the typical ones. It's not always a halogen, but it is oftentimes a halogen. An oxy acid, unsurprisingly, is going to contain oxygen. Those are the 2 types of acids, and we have to differentiate them because we have to name them differently. Okay, we'll go through the binary ones first. It's very straightforward. For a binary acid, you are going to first write down the hydro prefix. Okay, so literally I'll write down the letters hydro. Okay, then you're going to follow the hydro with whatever your non-metal base name is. Okay, we already talked about what base names are. So for HCl, your Cl is your non-metal. So the base name of chlorine is chlor. So you'd write down hydrochlor, then you'd add IC to it. So hydrochloric, then you'd write the word acid. So for a binary acid, you'll always be starting a binary acid with hydro. Okay. If you have an oxy acid, it's a completely different process to name them. Oxy acids are named strictly from the polyatomic ion that makes them up. Okay, so if you have whatever, you have to be able to name polyatomic ions in order to name your oxy acids. There's no way around that. If you have a polyatomic ion that has an ATE ending, you are going to simply remove the ATE ending and replace it with an IC ending and write the word acid afterwards. If you have a polyatomic ion that has an ITE ending, you are going to remove the ITE and replace it with an OUS. And that's how you're going to name oxy acids. Okay. We are going to look at examples of this though, so you can see it in action. Here's the summary. Okay, your hydro prefix means that it's a binary acid. If there is no hydro prefix, that means it's an oxy acid. If it's an oxy acid and it ends in IC, you have a polyatomic ion which ended in ATE. If your oxy acid ends in OUS, you had a polyatomic ion that ended in ITE. So we'll try these, starting with these three. The first thing that you can notice for all three of them is there is no oxygen present. That means all three of these are binary acids. So all three of them should start with the prefix hydro. Okay. The next part is knowing what the root name of each of the anions is. So you can look it up in the root table that I put into your slides. Take a minute and do that. Once you've looked up the root name for each one of them, you'll add the IC ending to the root, and you'll add the word acid afterwards. Okay, you'll notice that the only difference between what you might have expected and what you wrote down in the first one here is that when you have something like hydriodic acid, instead of writing hydroiodic acid, it gets a little bit combined. But if that's the only difference between what you wrote down and what I wrote down, then you understand the process and you are doing the right thing. Okay, let's look at some more examples. In each of these cases, we're looking at acids that contain oxygen. So they are oxy acids. So we're going to be naming them strictly based off of the polyatomic ion names. That means that you have to be able to identify what this polyatomic ion is, what this polyatomic ion is, and what this polyatomic ion is. Okay? If you can't do that based just on memory, then you have a lot more studying that you need to do. Okay, you have to know each of these polyatomic ions on site. You have to know what their names are. You have to know what their corresponding charges are. Okay, so this first one, this is an acetate ion. So to name it, it ends in ATE. So we want to remove the ATE ending and replace it with an IC ending. So the acetate ion becomes acetic acid. This ion right here, that's a nitrite ion. We're going to remove the ITE ending and replace it with OUS. That becomes nitrous acid. The NO3 ion is nitrate. We'll remove the ATE and replace it with IC. That becomes nitric acid. And we can go in the reverse direction as well. Here we have perchloric acid. So we can look at this IC ending here and know that IC is equivalent to an ATE ending of our polyatomic ion. Then we can go back and say, well, I know what the perchlorate polyatomic ion formula is. It's ClO4 minus. So the formula of perchloric acid must be HClO4. Okay, you can do the same thing for chloric acid. Chloric ends in IC. That means we must be looking at the chlorate ion, ClO3 minus. So the formula for chloric acid is HClO3. Okay, pause it right here. Take some time to fill out this table. I'm going to put up the answers, but I would like you to try them on your own before you looked. Note any that are giving you trouble. Okay, now we're combining everything in these sections. Same thing over here, we're combining everything. We've got a mix of all types of naming going on here. So pause this, try these out. And when you're ready, you can move on. Okay, one thing you do want to be reading a little bit about is how acidic components in our environment can cause things like acid rain. It might be a good idea to look at the particular pollutants that do combine with water to form the acid rain water. We definitely be reading over that section, okay? Read over the pollutants that cause acid rain and the acids that they form. And this is the actual flow chart for all of your inorganic compounds. Now, this flow chart, I feel like it looks scarier than it is, but this is only to tell you kind of what to do every time you're faced with a naming question, okay? Because when you were given a compound and they're like, name this compound, well, the first thing you have to do is answer this question. Is it ionic? Is it molecular? Or is it an acid? From that point, you can move forward, right? If it's an ionic compound, well, is it group 1 or is it group 2? And do the charges change around? If it's group 1, you name it this way: the cation and the base name of the anion. If it's group 2, you have to remember to include the charge of the metal. If you're dealing with a molecular compound, you're simply going to do prefix, name of the first element, prefix, name of the second element. And then if it's an acid, you want to figure out if it's a binary acid or if it's an oxy acid. If it's binary, it's going to have hydro, the base name, and the acid. Whoops. If it's an oxy acid, this is what your ATE ending will look like. This is what your ITE ending will look like. All right, so that flow chart is just there to kind of walk you through the process of naming if you don't have all the rules clear in your head yet. So it might be a good idea to start out trying some of those problems with this flow chart in front of you and letting it guide you through the questions until you're comfortable tackling them on your own. Okay, so that's it for naming. I'll be finishing up later today with the organic compound section.